Hi. So in this podcast, we're going to look at some basic concepts of thermal physics involving heat and temperature. We're going to understand the difference between these two related but different ideas. We're going to look at the theory behind and the application of thermometers as a way of measuring temperature, including knowing the difference between the Kelvin and Celsius temperature scales. We're going to briefly look at the connection between heat and work, and we can see how friction as a problem, so to speak, can be solved using the kinetic or particle model of nature. So let's start with our first basic concept, and that's this concept of internal energy. Every object, every liquid, every gas, every sample of matter in the universe has internal energy. That internal energy stored within that sample, object, whatever, comes in several forms, and those forms are shown on this diagram. On the top row, A, B and C on this diagram, we have forms of kinetic energy. The particles, be it atoms or molecules, just moving around, that's called translational motion. Within a molecule where there is some bonding, the different parts of the atoms can be rotating, or they could be just spinning. That's rotational motion. And then again, really, if you've got bonds, then the particles can be moving within, stretching and squeezing those bonds. And the movement of the particles is vibrational motion. So translational, rotational, and vibrational. But they're all kinetic energy. They all involve movement. The two forms of potential energy are on the bottom row, and they are intramolecular potential and intermolecular potential. Now, this is the last time in this topic that we'll mention intramolecular, because that's going inside the molecule. In other words, we're looking at the chemical bonds. And the only way that chemical bonds are released and broken and changed is in a chemical reaction. And we'll leave that one to the chemists, okay? However, the intermolecular bonds we can look at. That's physics, because that's about freezing, it's about boiling, it's about cooling, it's about condensing and sublimating, it's about all of these processes. So, to go back, translational and potential. Solids obviously have significant amounts of potential energy and less kinetic energy. Liquids, more kinetic, but still a lot of potential. Gases, very little potential energy. The bonds between particles are very, very weak in a gas. In an ideal gas, which is a particular model of a gas we'll use, we'll say there are no bonds, and therefore ideal gases have no potential energy and only kinetic energy, something that will become very important later in the topic. So the internal energy, which is given the symbol U, equals the total kinetic energy plus the total potential energy, and the units of internal energy and kinetic and potential energy are, of course, joules. Temperature. So what's temperature? Temperature is a measurement of the average kinetic energy of the particles in the sample. It has nothing to say about the potential energy. It is only interested in the kinetic energy. Two objects or two samples with the same temperature will have exactly the same average kinetic energy. Notice I said average. The actual kinetic energy of the particles will vary. There will be a distribution, as we'll see later, but the temperature is equivalent to the average kinetic energy of the particles. Temperature also measures the direction of energy flow, which we'll look at later. Right, we'll look at it now. If two objects that are at the same temperature are not necessarily going to feel at the same temperature to your body. If you pick up something that's metal, and if you pick up something that is cloth or wood or some fabric, then they might well feel to be different temperatures even when they're at the same temperature. If you look around wherever you're sitting right now, then you'll see many objects that unless they're generating their own heat, will probably be in equilibrium with a room. Books and desks and furniture and chairs and whatever. But touching them will feel different. That's because it's actually when you're touching something, you're feeling the temperature of your hand. Now you are warmer than most objects, and so they will conduct the heat away from your hand. Something that's metal is a good conductor of heat, so it will feel colder. Something that's cloth or fabric, like the books, is not a good conductor of heat, and therefore it will feel warmer. So if your hands aren't a very good measurement of hot and cold, then how can we measure temperature? Well, we need two things. We need a scale and we need a thermometer. To have a scale, we need fixed points that everyone agrees on. Everyone can't have their own individual temperature scale. Everyone needs to agree on the temperature scale. So you need two fixed points, and you need to decide on a number of divisions between those 2 points. To create a thermometer, you need some physical property that changes with temperature in a predictable, repeatable way, and you need to calibrate it against your fixed points in the temperature scale. Okay? So the fixed points for Celsius, which is a temperature scale you should be familiar with, are basically melting ice at 0 and boiling water at 100. Nice and logical. Fahrenheit also has fixed points. You may have heard of Fahrenheit. What those fixed points are is not quite so obvious, but the fixed point of 0 for Fahrenheit was actually the coldest temperature, which was kind of ice and salt mixture, that Dr. Fahrenheit could make in his laboratory. He reckoned that was the coldest temperature there is, so he wanted to avoid negative temperatures, so he made that 0. 100 degrees on the Fahrenheit scale was meant to be human body temperature, but perhaps the guy had a bit of a fever at the time because human temperature is not quite, body temperature is not quite 100 degrees. Close, not quite. Physical property, well, this is your standard, normal, what you think of as a thermometer. A liquid could be mercury. Nowadays it's more likely to be alcohol because mercury is rather poisonous. And as the thermometer and the liquid inside it gets hotter or colder, it expands or contracts. Okay, and the amount of expansion, the amount of contraction is measured on the scale, and that gives you the temperature. So here we have an example of that in use. On the left we have some ice, and you'll notice that it registers as 0 degrees Celsius, which is about 32 degrees Fahrenheit. And on the right you'll see some boiling water, which is at 100 degrees Celsius on the right side, and on the left hand side 212, I think it is, degrees Fahrenheit. So the temperature scale for Celsius, 1 degree C, is 100th the difference, the temperature difference between the freezing point and the boiling point of water. Okay, so the freezing point is one fixed point, the boiling point is another fixed point. You divide that into 100 times. Except that's not true, not since 1954. Since 1954, we've actually operated on a different temperature scale, namely the Kelvin. And 1 Kelvin is 1,273.16th of the temperature difference between absolute 0 and the triple point of water. Now, absolute 0 is the coldest temperature you can get. We'll look at that more later, and it's equivalent to minus 273.16 degrees C. So that's the 0 point. You can't get any colder than that, so Kelvin starts at 0. The triple point of water, well, the triple point of water is a little bit more difficult to explain. The triple point of water, here, we'll mention it. The triple point of water is a point of water at which ice melts. And when ice melts, it becomes also a gas. It starts to evaporate. So at 0 degrees, ice exists as solid, it exists as a liquid, and it exists as a gas. Hence, triple point of water. So, triple point of water and absolute 0. So that's the definition of 1 Kelvin. Now, 1 degree C is simply, the temperature in degrees C is simply the temperature in Kelvin, either add or subtract 273.15. Okay, that's how you convert the two. If you have the temperature in degrees C and you want to know it in Kelvin, you add 273.15. If you know the temperature in Kelvin and want to know what it is in degrees C, you subtract 273.15. But the actual defined unit, the SI unit, is Kelvin. Celsius is a derivative of that. So as I said, at different temperatures, temperature is a measurement of kinetic energy, okay, and kinetic energy obviously is based on the velocity. What the actual reason for this graph is, it shows you 4 different temperatures, and it shows you how at different temperatures in Kelvin, between 300 Kelvin and 1200 Kelvin, for a gas sample, the velocity changes, the average velocity changes. The point there was that as you get colder, that average drops, so it gets towards 0. At 0 Kelvin, the average theoretically will be 0 meters per second. We can extrapolate back, so we collect data points on the right hand side, and we can draw a line back, and the graph will reach 0 at minus 273.16 degrees C. Temperature point of water we've mentioned. Converting again between Fahrenheit and Celsius Kelvin, we have absolute 0, 0 Kelvin equals minus 273 degrees C equals minus 459 degrees Fahrenheit. Water freezes at 273 Kelvin, 0 degrees C, 32 degrees Fahrenheit, and boils at 373 Kelvin, 100 degrees C, and 212 degrees Fahrenheit. So these are all just different temperature scales. Kelvin is better than Celsius, better than Fahrenheit in a very definable way. It starts at 0. Okay, and that's very important for many of the proportional relationships that you'll look at in this topic. Many properties are proportional to temperature, but only when you measure the temperature in Kelvin, only when you measure it in a scale that starts at 0. So how do we make things hot? Well, we have to do work. For example, this diagram you may remember seeing before, it shows a boy pulling a sledge. He's doing work. He's spending energy. Where is that energy going? It goes into kinetic energy. But where does the energy go? He keeps on supplying energy, but the kinetic energy of the sledge stays the same. So in other words, the extra energy must be going somewhere, and what it does is it goes as heat. It heats up him, it heats up the sledge, it heats up the surroundings. The work, where does the work go? It goes into heating up the area, particularly by friction. Okay, if you rub your hands together, your hands will get hot. You're putting the work in, it's going into the internal energy, it's increasing the translational motion, the rotational motion, the vibrational motion, and therefore it's increasing the temperature. If you put in enough energy, it might cause the potential to change. Ice might melt, water might boil. But you are putting in the energy and it's going into the object, it's going into the internal energy. So what is heat? What is heating? And the answer to that question for me is that heating is a process. What is heat as a noun? Heat is the energy that is transferred. It's just a measurement of energy that's being moved. And I prefer to think of it as a verb, to heat something. Okay? What does an object have? Whether it is hot or cold, it has internal energy. Part of that internal energy is the kinetic energy, and that kinetic energy determines the temperature. Okay, but it doesn't have heat. Heat is a meaningless concept for something to have. Heat is something that is moved. Heat is something that is transferred. Okay, so we've understood the concepts of temperature and heat, two very different things. Heat is energy transferred. Temperature is a measurement of the average kinetic energy. Using a thermometer we've discussed, and the difference between Kelvin and Celsius you should now know. The connection between heat and work. You do work, eventually it ends up as heat, always. Often friction is the process. But speaking of process, how exactly does heat transfer? We've said heat is transferred energy. How does that happen? Well, that's what we're going to look at next. Thank you very, very, very much.